Good morning everyone. My name is Ambanishri. I am from CSM E section and my roll number is 25. Today I will be discussing topic Cayley-Hamilton theorem for robotics. The Cayley-Hamilton theorem is not only for mathematics, it is also used in robotics. Let's see. Introduction to Cayley-Hamilton theorem. The Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic polynomial. Yes, if the characteristic polynomial, that is lambda cube minus s1 lambda square plus s2 lambda minus s3 is equals to 0, if lambda equals to a, then that matrix satisfies its own characteristic polynomial. And the second point, this theorem is significant in control theory and robotics for analyzing system dynamics. Yes, this Cayley-Hamilton theorem is important in control theory of robotics for analyzing the dynamic systems. And understanding this theorem is essential for designing stable robotic systems and controllers. Here is the example in mathematics. We can see that matrix using Cayley-Hamilton theorem. See, the characteristic polynomial. The characteristic polynomial of a matrix is defined as a p lambda equals to det of a minus lambda I in the sense unit matrix. So it provides important information about the eigenvalues of the matrix. This characteristic equation defines the importance of eigenvalues of the matrix and also information about the eigenvalues. For a n times matrix, the polynomial of the degree is n. Here we can see a matrix A equals to 2, 27, 0, 0, 4, 40, 0, 3, 30. And our unit matrix is I 1, 0, 0, 0, 1, 0, 0, 0, 1. And the lambda I equals to lambda 0, 0, 0, lambda 0, 0, 0, 0, lambda. So here in the right, P lambda equals to det of A minus lambda. It is the characteristic equation. Okay, by solving this we get the polynomial characteristic polynomial. The Cayley-Hamilton theorem, it also applies in robotics. In robotics, the dynamics of a robot can be modeled using state space representation. The dynamics of the robot can be modeled using this state space representation. It is also there in Cayley-Hamilton theorem. The state space representation often involves matrices that can be analyzed with the Cayley-Hamilton theorem. Just now we discussed that state space representation also involves matrix that can be analyzed with the Cayley-Hamilton theorem. This allows robotics to predict the behavior of robots under various control inputs. This application allows the robotics to predict the behavior of the robots under the various control inputs. So this Cayley-Hamilton theorem is used in robotics. Here is an example of 2 by 2 matrix such that A is not equals to 0 but A square equals to 0. Let A equals to 2, 1, 6, 3. Find the 2 by 2 matrices B and C such that AB equals to AC, but B is not equals to C. And also third, A equals to some 3 by 3 matrix and B is also 3 by 3 matrix. Multiply A and B. Use the column representations or row representations to product these A and B matrices and Show that if the column of a B are linearly dependent, then so are the columns of AB. Show that if the rows of A are linearly dependent, then so are the rows of the AB. Okay. Let A equals to some 2 by 2 matrix. Compute a formula for A to the power n greater than or equals to 1. Here verifying the Cayley-Hamilton theorem. For example, the given matrix A equals to 2, 1, 2, 5, 3, 3, minus 1, 0, minus 2. Yes, we know that the characteristic equation of A that equals to det of A minus lambda I, that is equals to 0. So here A equals to 2, 1, 2, 5, 3, 3, minus 1, 0, minus 2. And the I, that is unit matrix, equals to 1, 0, 0, 0, 1, 0, 0, 0, 1. We know that characteristic equation of the given matrix is lambda cube minus S1 lambda square plus S2 lambda minus S3 equals to 0. This is the characteristic polynomial. Since S1 equals to trace of the matrix, trace of the given matrix. Trace means sum of the principal diagonal elements, and S2 equals to cofactors of principal diagonal elements, and S3 equals to det of A, det of the given matrix. Here example, A equals to 2, 1, 2, 5, 3, 3, minus 1, 0 and minus 2. And the characteristic equation A equals to det of A minus lambda I. Here the characteristic equation we get this matrix 2 minus lambda 1 2 5 3 minus lambda 3 minus 1 0 minus 2 minus lambda, that is equals to 0. And by the characteristic polynomial lambda cube minus S1 lambda square plus S2 lambda minus S3 equals to 0, we got lambda equal lambda cube minus 3 lambda square minus 7 lambda minus 1 is equals to 0. As we discussed, according to the Cayley-Hamilton theorem, lambda equals to A, that is A cube minus 3A square minus 7A minus I equals to 0. This is the second equation. So find A cube and A square and substitute in the equation 2. Here A cube equals to 36, 22, 23, 101, 64, 60, minus 7, minus 3, minus 2. And also we have A square. And also we have A matrix. So substitute all this A cube, A square and A and also unit matrix in the second equation. Then we got the 0 matrix. Hence the Cayley-Hamilton theorem is proved. Control systems in robotics. Control system often rely on the stability and controllability of robotic systems. The Cayley-Hamilton theorem helps derive system responses using state feedback. By understanding how matrices behave, robotics can design more effective controllers. By understanding our matrices, they can design more effective controllers in robots. Dynamic modeling. Dynamic modeling of robotic manipulators often involves differential equations represented by matrices. The Cayley-Hamilton theorem allows for the transformation of these equations into the manageable forms. This process aids in the simulation and control of robotic arms and other systems. Cayley-Hamilton theorem is used for the dynamic modeling for robotics. Advantages of Cayley-Hamilton theorem in robotics are: the Cayley-Hamilton theorem simplifies calculations involved in control design. It enhances the understanding of system stability and response characteristics. This knowledge is vital for developing robust robotic systems that perform reliably. And the limitations of using the Cayley-Hamilton theorem in the robotics. The theorem applies only to square matrices, limiting its direct application. So this theorem will not apply to 3 by 2 matrix, 1 by 2 matrix or 2 by 3 matrix. This is only applicable for square matrix like 3 by 3, 4 by 4, 2 by 2. Non-linear systems require additional techniques beyond the Cayley-Hamilton theorem. Understanding these limitations helps robotics select appropriate modeling techniques. According to this limitation, the robotics selects appropriate modeling techniques in manufacturing of the robots. Real-world application. Here the theorem is applied in robotic navigation and motion planning algorithms. The Cayley-Hamilton theorem is applied for robotic navigation, and it is also utilized in the design of adaptive controller for dynamic environments. These applications showcase the practical importance of the theorem in robotics. Here the Pythagoras theorem, c square equals to a square plus ab, a equals to under root c square minus b square, b equals to under root c square minus a square, c equals to under root a square plus b square. This is the real world applications of Cayley-Hamilton theorem in robotics. Future directions of the Cayley-Hamilton theorem in robotics are: the future research may explore the extending the theorem to non-linear and hybrid systems. Integrating the Cayley-Hamilton approach with the AI techniques could yield powerful robotic systems. Integrating means improving or developing this Cayley-Hamilton approach with the AI techniques could yield powerful robotic systems in the world. Continuous learning from real-world applications will help refine these theoretical concepts. And the conclusion is, the Cayley-Hamilton theorem is a foundational concept in linear algebra with broad implications in robotics. Understanding and applying this theorem can enhance robotic design and control. As robotics evolves, the integration of these mathematical principles will remain crucial. Yes, this is true. Thank you.